Hello, students. Let's talk about work and energy. All right. What we need is a bit of a foundation into what it means for there to be work done on an object or work done by a force. Well, what that means is that by definition, the work done by a force on an object is the force times the distance through which the force acts. Now, sometimes you will see, I'll make notation like that, which means something real important, that only the component of F parallel to delta x does work. And what I should say is that F and delta x are vectors. All right, so for an object that that experiences, let's call it a net force F, and moves through a distance or through some change in position, delta x, the work done by the force is the magnitude of the component of the force that's parallel to delta x and delta x. So, let's say that we have a force versus position graph that is simple and looks like this. That a constant force is applied to an object. So what this might look like is here is an object. There's a force F that happens to be parallel to this vector delta x, and the object moves from one place to another because of that force. Let's just say that force is constant, and well, let's say that there is some delta x. Since work is F times delta x, then the work is that value F times this displacement delta x. That happens to be the area under this non-curvy curve. The area under the curve is a typical way of stating that. Okay? So for this one, important to be able to recognize that work here is area. Now, force measured in newtons, position measured in meters, that area will have the units of Newton meters, which we call a joule, capital J. Okay? Now, what's the result of doing this work? Well, in this case, if we say that F is the net force, the sum of all the forces acting on this object, what this object will do is speed up. If that is one force acting on this object, and there might be, say, a friction force also acting on this object, well, that frictional interaction can create can increase the internal energy of both the surface across which this object slides and the object itself. Internal energy can increase, and that means the objects will get warmer, like rubbing your hands together, generate some increased thermal energy. All right. You can also hear that stuff happens. That would be some sound energy being, I guess you could say, created from the physical interaction of the two objects. Okay, so the bottom line is that this work always results in a change in energy. Okay, that's called the Work-Energy Theorem. Now, depending on what force you're talking about, there can be different amounts of energy change. All right, if we're talking about the net force, well, that can only accomplish a delta K. Parts of forces that act on objects, or parts or components of the net force, I guess I could say, can result in different kinds of energy transformations. All right, so we'll talk about a few of those cases. But bottom line is that's how we can express how much work a force does, and here's what work always accomplishes. All right, let's look at a case like this. Well, we have an object and it's held, let's say held a distance h above the Earth. And here's the Earth. And we're going to look at this from two different perspectives. And depending on how we want to define our, quote, system, well, we're going to talk about some different results that yield the same result. All right, and so if our system here in case one, let's say this is our, quote, mass, and our system is what we'll call the Earth mass system. Both the Earth and the mass and this mass are parts of our system. So if these two things are part of the system, well, here's a force mg that acts on that object. All right, that's a gravitational force exerted by the Earth on the mass. All right, it has magnitude m, if this thing has a mass we'll call m, times the Earth's gravitational field strength or gravitational acceleration, depending on how you want to define g. Well, that force is the force that one part of the system exerts on the other. So what we would say here is that there are no external forces. External means forces applied by things that aren't part of our system. So what we can probably actually do is talk about, we should say work done by an external force. Work done by some force that, or work done by some object, a force exerted by some object that isn't part of the system of objects you're talking about. All right, so here, if the Earth and mass are both part of our system, there are no external forces. And that means that, well, the work done on the system is zero. And it means that the change in total energy of the system is zero. And what that means for us is we can say that the system's initial and final energies are the same. Now this system, we can characterize its energies as mechanical energies. From here on, I'm assuming that you might have a background in mechanical energy. My dudes do energy first and then work. All right, so if we talk about this system's mechanical energy, well, we can say there's, well, typically I would say kinetic energy, and that's my notation, our College Board's notation for gravitational potential energy, UG, K initial plus UG initial, K final plus UG final. Notice we're saying the energy is always constant because there are no external forces doing work, so there's zero total change in energy. The energies are equal at any instant. All right, let's say we drop this thing from rest. That goes. Let's say we want to know the speed just before this thing hits the ground. Just before it hits the ground, that thing goes. We get mgh is 1/2 mv final. M's go, and if we felt like it, we could write an expression for this object's velocity at the instant before it hits the ground, radical 2gh. Yeah? Now look at this. If we say that in a different case, it's the same situation, but we define our system as only the mass, well, then the Earth is not part of the system that we're talking about. And this force mg that is exerted by the Earth, now, the Earth is still there. The Earth still does what Earth does. The Earth still creates a gravitational field, which in this case exerts a gravitational force on our mass m. It's just that the Earth isn't part of the system of objects that we're talking about. So this mg is an external force. So now in this case, hang on one sec. Just giving myself a little extra room. In this case, we do have work done Ooh, we do have work done by our external force, and that's F parallel times delta x, and that equals delta E total, the change in our system's total energy. All right, well, this force that acts is force mg. And here is a vector delta x. Well, the magnitude of that vector is still h. Well, what happened there? What is going on here? Get over there. Okay, so through a distance delta h equals delta E total. Now here's a tricky thing. The energy, the only energy that this object can have the only energy this object can have is kinetic energy. All right? And that seems perhaps a little strange because, well, how is there not mgh? This thing has a mass. Earth makes a field g and h is h, right? Except here's the deal. If we're not calling the Earth part of the system, gravitational potential energy only exists when one object is in the gravitational field made by another object. Right? If the Earth's not part of our system, then there is no system of objects where one's in the other one's field. So a single mass can only have kinetic energy, the energy of its own motion. It can have internal energy unless we consider this thing a point mass, which is what we're going to do. It's not. We're going to neglect its what we call internal structure. Forget about the fact that this mass is made of other parts. It's just a thing. All right. So without the Earth as part of our system, there can't be UG. There can't be gravitational potential energy because that has to be of a two-object system, where typically the Earth is one of those objects. All right, so this says mgh is k final minus k initial. That's delta k. K initial is still 0. This thing's dropped. And look, we get mgh is 1/2 mv final squared. And our masses go, and we get again that, well, sure, of course. It better be the same answer, right? A minute ago, we looked at that from a different perspective, where we looked at this system of objects as the Earth and the mass together, where there can be gravitational potential energy associated with those two objects. But when we say it's just the mass, well, the difference is now there is work done by gravity. In case one, there is no work done by external forces because the Earth's part of the system. So what's neat is, if you're careful about how you approach definition of your system, and therefore definition of, or identification of what forces are internal or external, you get the same answers. Okay? All right. Now, let's look at a different, well, let's see. Let's say we have a force that's what we call position dependent. Force versus position, and let's say this thing does that. Okay, just so we're sure, we can still say if this force acts over some, well, let's call it a distance d now. Well, there's two ways of doing this. Work equals, we can't, well, we say F times delta x, but when the force is a non-constant force, one thing you can do, particularly when forces vary nice and constantly like this, is we can find the average. Right now, we're still assuming there's a parallel in there, and that this is a representation of a force that's component of a force that's parallel to our displacement delta x. So what we can do is say there's the minimum, there's the maximum, there's the average. So we could say that we take that average force times that distance d, probably closer up there. Yeah, that's good. All right. But what I want you to notice is that this area, right, has like this extra part above the red line, but is missing this part below the red line. All right, so the area of the blue shape and the, well, really the area of the red shape here are the same area. The area of the red shape is quite literally the average force times the displacement, and the area of the blue shape is the area of the blue shape, but same thing, work is the area under the curve. And result, same thing. This work will accomplish some change in system energy. Here's a certain kind of specific position-dependent force. This is the work done. We're going to look at the work done by a spring on a mass. So here we have a spring that's compressed. Here we've noted or identified this, I guess the mass's equilibrium position. All right, so when the mass is at that position, the spring is not compressed or stretched at all, and therefore applies no force. All right, and let's look at force applied by the spring as a function of position. And we'll call this, how about initial and final? So initially, I'll say that the spring, how about we say, is compressed that much. There's a x initial. And in the end, the spring is extended that much. There's an x final. All right, x talks about change in spring's length from its equilibrium position. All right, well, as some of you might know, the force that a spring applies to an object goes like this. If we talk about this as a vector equation, the force that a spring applies is, well, this part means proportional to its displacement, but always in the opposite direction. So in our initial case, the spring is displaced to the left, and that means that the spring pushes to the right. In our final case down below, the spring is displaced to the right, so pushes back or pulls back to the left. But notice, x initial is bigger than x final. So that means that the force is smaller. It's okay? So if I say initially, how about that? Here's an x initial. I've made it negative because I'm saying in a coordinate sort of system, that's a negative direction, that's a positive direction. Our initial x is to the left, it's negative. And I'm going to say that there's some initial spring force, I'll arbitrarily call it that. Now at the end, in our final position, let's call x final about there. It's less than x initial by a factor of 2-ish per the diagram, right? So here's f initial. Well, f final, here's a point that I know is on this graph. When the spring is not compressed or stretched at all, the spring applies no force at all. And the nature of this equation says that this force versus position graph is linear, so it goes linearly through the origin and then stops there, and then that means this is our final spring force. You with me? So, we can talk about the work done by this force. All right, and if we want to do that, we can say, well, there's an area of this shape. There's an area of that shape. The area of, I'll do it in red, the area of this shape is the area of a triangle. So let's call this about part 1. So the work done in part 1 is the area of that triangle, which is 1/2, well, the base is x initial and the height is f initial. Well, the f initial is, f is kx. So we say kx initial. And the question is, how come you're not using negative? It says negative. That part is about the direction of the force. Okay? And, well, we don't have to account for that when we account for the size of this force. Okay? The direction doesn't affect the size. All right? So this work done in the first part is 1/2 kx initial squared. Well, the work done in the second part is 1/2 a base times a height, and that's a 1/2. Let's see, our base is x final, and our height is f final. That should be a final there, f final, and that's 1/2 x initial times x final and kx final. Now, we do have to say, though, that if this is a positive area above our x-axis, this is a negative area. Okay, so if we're saying that in our initial case, as the spring moves the object this way, the spring pushes this way, and the object moves this way, that work done is positive. In this case, as the object moves this way, but the spring pulls back this way, that work done is negative. All right, so this we're going to call a negative area, and this work done here, work 2, is negative 1/2 kx final squared. So the total work done is the sum of those two works done, and the work done total is 1/2 kx initial squared minus 1/2 kx final squared. Whoops, final squared. Now, if you have a background in energy so far, you know that that is the potential energy stored in a spring. Let me shrink this stuff up. Oops. Whoops. So what we have is our work total is the initial spring energy, potential energy U spring, U spring initial minus U spring final. Or the work done, the total work done, is negative delta U spring. Now, that's supposed to go in this in this ungroup. Remember that result. There are certain cases in which the work done by a force is equivalent to the change in potential energy. And importantly, the work done decreases the potential energy. That's the definition of something important. So keep your head wrapped around that while you can. Okay, so there's some tricky stuff here for sure with signs especially. All right, we should go back to this and make a definitional thing where we say that work done, well, it's important to talk about directions of F and delta X because really the work done by a force by definition is what's called a dot product of two vectors. Where by definition, if you want the dot product of two vectors, what you do is you take the component of, well, you take the magnitude of the component of one that's parallel to the other and you multiply those two magnitudes together. And what you can do to do that in a lot of cases is to take the magnitude of one times the magnitude of the other times the cosine of the angle between them. You might perhaps recognize that if we have a force like this and a delta x that goes like this, well, look, there's this angle theta between those two vectors. That angle theta also goes right here. So this force F parallel, and I mean parallel to delta x, is F cos theta. So when we do, generally, magnitude of F times magnitude of delta x times cosine of angle between them, in effect, one thing that we're doing is calculating the component of one thing parallel to the other, and then multiplying it by that other vector. Okay? So what this says is there are some cases like, right, we got that cos theta in there. When we have our case 2 here, right, this case here, I'm going to expand and add a page. We have the object, nope, we have the object that moves from here to here. That's the delta x. Well, the whole time that object is moving this way, there's a force on it. First a small force that way, then a bigger force, then a bigger force, then a bigger force. Those forces are always in the opposite direction of delta x. So when we talk about the work done in this case, we can say it's the magnitude of the force times the magnitude of delta x times the cosine of the angle between them. And that cosine of that angle, or the angle, is 180 degrees. So this work done is negative because the cosine of 180 is negative 1. The work is negative F delta x. In this case, it would be the average force because the force gets bigger and bigger and bigger the farther this thing goes. All right, so it is okay to have negative amounts of work done. And there are always negative amounts of work done by a force if the part of the force that does the work points opposite the direction the object moves. Okay, so a lot to digest there, but a good introduction to work, particularly as it applies to energy. Okay, and more to come.